Hi, welcome to office hours. Virtual office hours, that is. A regular feature in which we try to answer questions that you've brought up in the discussion forum. Questions that we think are important to your future work. First question for the day is, why is the magnitude of the derivative of a rotating unit vector equal to theta dot? Excellent question. One we're going to answer in some detail because in this course we're going to make great use of what are called body coordinate systems. In many problems, the position, velocity, or acceleration of a point is most conveniently described in a coordinate system that's attached to the moving body, so-called body coordinate system. And when you do that, you must take into account the fact that the unit vector is moving. So, watch this. In our use of polar coordinates, we encountered the need to evaluate the time derivative of a rotating unit vector. In this discussion, let's refer to the unit vectors as I hat and j hat, respectively. We know that the unit vectors are rotating with an angular velocity theta dot, and therefore have time derivatives di hat dt and dj hat dt, respectively. How do we evaluate these derivatives? In a time interval delta t, the unit vectors go through an angular displacement delta theta, and their tips go through a linear displacement di hat and dj hat, respectively. The magnitudes of these displacements are the product of the unit vector's length and delta theta. Since the unit vector's length is unity, the magnitudes are simply delta theta. In the limit, as delta t goes to 0, delta theta over delta t becomes the instantaneous angular velocity theta dot. di hat dt is in the direction of j hat, while dj hat dt is in the direction of minus I hat. This gives us the expressions needed to evaluate the time derivative of the unit vectors. All right, so there you have it. And in the future, if you can't remember the derivation, just remember the result. The derivative of I hat is equal to theta dot j hat, and the derivative of j hat is equal to minus theta dot I hat. All right, so the next question concerns the video on planar motion, in which it was stated that the angular velocity and the angular acceleration of a rotating body can be represented as a vector. And the question is, what good is that? And are we actually going to use that? The answer is, you bet. Vectors are a tremendously useful piece of analytical machinery that enables us to make calculations with standard operations very easily, and vectors keep all the arithmetic straight. So watch this. Rotation is a very common motion. When a rigid body rotates about an axis, all points on the rigid body follow circular paths about the center of rotation, which, by the way, need not lie inside the rigid body. All lines in the rigid body rotate through the same angle in a given time interval. That is to say, the entire rigid body has a single angular velocity omega. Angular velocity is represented by a vector. The vector's magnitude is the time rate of change of the angle with units of radians per second. The vector's direction is parallel to the axis of rotation. So in a fixed coordinate system, with unit vectors along the x, y, and z axes respectively, a rigid body rotating about the z-axis has its angular velocity vector written as omega equals omega k. For example, assume we were interested in the linear velocity of a point on the rotating body. When omega and r are perpendicular, the cross product is especially easy to evaluate. The linear velocity has a magnitude of omega r and a direction perpendicular to both omega and r. And on this third topic, degrees of freedom and generalized coordinates, there were a number of questions. So here we're going to work a simple problem through for you to help you understand both the underlying concepts and how they're applied. So watch this. Let's use this simple problem to talk about degrees of freedom and linked coordinates. Here's a system with two rigid bodies in planar motion, a mass and a pulley. The mass is constrained by two walls. The pulley is also constrained by two walls. The mass is connected to the pulley by a cable that wraps around the pulley and is fastened to the ground. There's no slip between the pulley and the cable, and the cable is inextensible. How many degrees of freedom does this system have? Because the system is restricted to planar motion, each rigid body begins with 3 degrees of freedom. x1, y1, theta 1 for the mass, x2, y2, theta 2 for the pulley. 6 in all. The walls constraining the mass prevent horizontal motion and rotation. The walls constraining the pulley prevent horizontal motion as well, leaving 3 possible degrees of freedom, y1, y2, and theta 2. But these remaining motions are not independent. The no-slip condition between the pulley and the inextensible cable imposes a kinematic constraint linking y2 and theta 2. This eliminates another degree of freedom, leaving 2, y1 and y2. Are y1 and y2 independent? No. It's clear that these coordinates are also linked by a kinematic constraint through the cable. So the system only has 1 degree of freedom. But how can we express this kinematic constraint linking y1 and y2? In other words, how does y1 vary when y2 is varied? A conceptual trick. Assume y1 remains fixed while y2 is varied. If the pulley is moved a distance y2 with the mass fixed, you can see that the cable's length would need to be increased by 2 times y2. This is in fact the distance the mass must travel since the cable is of constant length. Therefore, the kinematic constraint linking y1 and y2 can be expressed simply as y1 equals 2 times y2. All right, so there you have it. See you next time.